So I planned this talk with some time for questions. So if you don't ask any questions, I will fill that time with awkward silence. So please do ask questions as we go along. I've been talking about this topic before. Oh, this is me. Yeah, I work at Google. I work on some of our data structure libraries, networking, etc. I talked about this topic before a couple of times. Maybe a couple of you have heard me talk about this topic. I'm going to try to take a slightly different approach this time. My goal in talking about performance optimization has been, at least the last few years, that the approach to performance optimization should not be write your program, hope you get lucky. If you're unlucky, spend this heroic couple of weeks with a profiler and hoping you can fix any problems in your code. I think that is not a very productive way. We might feel very proud after squashing a space league after 2 weeks, but it's not a very productive way to go about things. So I think optimization should be done like code correctness, right? We should write programs that are mostly efficient by design instead of kind of bolting that on later. If you do it that way, hopefully we'll not get into these 2-week-long debugging sessions. Another thing I include in the goals here is to keep myself honest and keep ourselves honest. I'm going to look at what we actually do. So instead of telling you, you should do this, and then I do something else when I actually have to write our libraries, I'm going to show you what we actually do. This means that some of the code might be a little bit ugly. That's good, because that will hopefully incentivize us to make sure that we can do this in a prettier way sometimes. So we're going to look at some actual library code. I'm not going to talk about benchmarking. It's very important when you optimize things. You should benchmark things. There was a talk last year about this. Please watch that. That's great. Benchmark use criterion. OK. So I want to take a step back. And I want to take a step back from Haskell for a second and think about optimization in more general programming terms. So first, when we are going to optimize something, we should ask ourselves, where should we start? What's the biggest bang for our buck? So for example, should we take this little book called Hacker's Delight? It's like 100 pages of bit twiddling tricks. Maybe we should take that. The first thing we do, like find all our bit twiddling and make it even twiddlier. Should we, if you write Haskell, write code and take bang patterns, put them randomly everywhere? Should we convert all our for loops to while loops? What should we do when we optimize? You are probably aware that modern CPUs, their performance is controlled by memory accesses. How we access memory, how much of it we access, etc. So kind of our hunch going into this is we should start with memory and think about how we access memory. The bit twiddling will be the last 10%. We may do that eventually. This is not this talk. We're going to start with the biggest hammer and try to hit the biggest nail. So we're going to look at memory and think about memory. That's kind of abstract. So how do you write a program that makes good use of memory? Right. So here's one way to approach that problem. We can look at languages which are fast and then say, what do they do with memory? And see if we can apply that to whatever we're doing. So I picked on C++ here because this quote happened to fit what I wanted to say. So this is Go for C++ language. So Bjarne is its creator. He says C++ should have zero-cost abstractions. And by that, he means two things. So one is, if you don't use the abstraction, it shouldn't cost you. We'll put that aside. It's not really relevant for this talk. That's a good feature of a language, but that's not the important part. The other part is, if you use abstraction, and then, again, talk about abstraction in kind of general terms, it should not cost you more, ideally, than if you hand-coded whatever the abstraction did for you. So for example, in C++, there's a vector class, which is an abstraction over arrays. You can do the same things with the vector class that you can do with arrays. And the goal here, if this is true, is using the vector class is no slower than taking the raw array, doing banging on pointers, and doing the kind of low-level twiddly things you might do. So if that is true, we have a zero overhead abstraction. C++ does this a lot. C++ is fast. So maybe there's something to this idea. So let's apply it to some abstractions. This happens to be Haskell code. These could be Java classes or some other language. I'm trying to kind of abstract from Haskell. I just needed some syntax. So here's some Haskell code. Here's an rewrite you might do, right? You have implemented a data type for lines. There's like 4 coordinates. You say, like, well, that's a bit silly. Clearly, lines are 2 points. Introducing this abstraction of a point is useful. Our code will be neater. It's clearer. We can, raise our abstraction level. We can talk about points instead of, 4 coordinates. So you might do this rewrite. Now, if we do this rewrite, we might ask ourselves, are these equivalent from a performance perspective? Well, the first point is, it would be nice if they were, right? Because if they're not, we're in this uncomfortable situation. We might have to write the topmost thing while we would like to write the bottommost thing because there's a trade-off. So we would like it to be the case that these are somehow equivalent from a performance perspective. And they will be or will not be depending on how we decide to represent these 2 data types in memory. And there's 2 fundamental representations. Unfortunately, one is usually called a value representation, which is a bit overloaded in Haskell because we use values to mean something else. But think about it as an inline representation, right? All the data for the aggregate type, the line type, is intermixed with the data for the point. Another representation, which I call the reference representation, is the line data type is over here on the heap somewhere and it has references or pointers to other heap objects over here, which are the points. So these are our 2 possible heap layouts we could have for aggregate data. What are some of the problems? Some of them might be obvious, but I think I'll go through them anyway. So on modern CPUs, if you have your data spread over the heap, you will load the line heap object into cache to get to the pointers, and then you have to follow the pointers to load the 2 other heap objects. That might result in cache misses because, especially in a garbage collector language, once the garbage collector has run, especially if it's a copying collector that does kind of a breadth first search, it might have scattered your objects all over the heap. Even if you happen to allocate them together, which often does, it will have scattered them after a GC. So that will incur cache misses, which we know is bad for modern CPUs. And then it's wasted space. So we had to store the pointers. That's some waste. In a garbage collector language, we typically have an overhead per heap object. We need to store some GC information in a header. So that will be wasted space. Since the cache size is finite, wasted space means less cache space left for useful stuff. OK, so again, remember, we're trying to talk a little bit more in abstract, because I want to make a point here that what we're going to do in this talk is not specific to Haskell. In fact, it's a kind of a trend in programming language design in general. So here's a mostly incorrect history to programming languages. There's a few programming languages scattered on this line. I wanted to capture kind of 2 groups of languages. There's a third, like the dynamically typed ones are kind of missing. But there's 2 groups here. There's kind of a explicit memory layout control group of languages. They're typically older, right? It was more important to do it back then, well, so it seemed. And then there's kind of newer kind of languages. They're dominated by the object-oriented camp, but there's also Haskell is in this group, where at least initial implementation, almost all values were represented with this reference heap layout. Now, what happened? The languages that decided that we're going to use this everything is pointed to the heap layout came to change their decisions, or at least add more control as time went by. Java here is question mark. Guy Steele has a proposal for adding, I think he called them value classes or something similar to Java, to be able to pick between these 2 different heap layouts. So I guess this is to say that being able to control this memory layout is an important kind of consideration for languages in general. Like, this is such an important optimization that independently or semi-independently, languages that didn't have this feature ended up adding it later. Oh yes, essential. People seem to agree on this. OK, so zooming back into Haskell and GHC, so we have this idea that controlling the layout of memory might be important. Lots of language designers seem to think so. Fast languages seem to do it. So let's see what we can do in Haskell. So first, kind of a little bit of a primer. This is a simple version of DHC's heap layout. What's up here is what's actually on the heap. That's what's expensive and costly. Sorry? Yes?
No, if I can control the memory, those other languages, or at least many of them, I can do polymorphism and memory layout.
Maybe. Yes, I think it should at some point. So we'll hopefully get there. Just the main, this is very typical for a GC language, right? There's the actual data, this is the payload, and then we need some extra metadata. It needs to be there for the GC. In a language with algebraic data types, we need to have a little tag bit that says, which constructor is this, etc. And then there's this kind of statically allocated part. If there's a closure, this will be the code that needs to be run in the closure. As I said, the tag bits and the GC info is here. Okay, clear so far? Okay, good. We can split our values, and here's where the word values gets a bit overloaded. Our kinds of heap objects into two groups, or rather, our kinds of values into two groups. There are what we call unboxed types, right? And you saw them a little bit in Simon's talk earlier today. These are the int hashes, right? The word hashes, the float hashes. These are representations of machine values, right? Some things you could put in a register or maybe on the stack, for example. These are the primitive values. And then we have the boxed values. And I think the boxed word comes from that. You can put it in a heap and it's a little box because it contains a little header and then the content of the box. So we call these boxed values. And boxed values is everything else, right? These are the normal data type we declare, and they can refer to other boxed values, which can refer to more boxed values or primitive values. And here's a little example to hopefully make that clear. So there are two types of values on this code snippet, right? We have the boxed ones that live on heap. These are the ints, right? So in GHC, in GHC, the int type is nothing magical. It's not baked in. It's just a data type declaration. It looks exactly like this. The hash here has no specific value. It's just kind of a convention we use for constructors that wrap primitive things. So int hash here is a primitive thing. It's a God-honest machine integer value. Cannot exist on the heap by itself. It needs to be wrapped up in a box like this. The representation of this value on the heap is this header. And I take it as a convention to write the name of the constructor in the header. It's just to kind of, when we have several of these on the screen at once, I would like you to be able to see which boxes represent which values. But that's the header word. That will be the pointer to this static information we saw on the screen before. And then we have, next to that, the real integer, the integer we care about. Is it clear so far? Good. All right, so now comes the controlling layout part. So on the upside, Haskell has had the ability to control memory layout a bit longer than say, Scala and Java. On the other hand, we have maybe the most ugly way to control the layout. So if you have a data type here, I've wrote this data type T, which is equivalent of an int pair, right? I've just written it out. It has this representation, the second, these boxes over here. It's going to be 1, 2, 3, 4, 5, 6, 7 words on the heap, spread out this pointer style representation we saw in the beginning. And if you want to say, no, we don't want this pointer style representation, we want the value style representation, we can do this. We say, unpack this int, which basically means, remove the box. So take this box and shove it in here. And while you shove it in there, you lose the header. We don't need it, since we only need one header per heap object. So once we moved the int from up here down into here, we don't need the header anymore. And we do that for both values. So we kind of shrunk down the size to 3 words and no pointers. Yeah. Yes, good point. So I'm being a little bit loose with strictness annotation in this talk because I didn't want to get them intertwined, but we can only unpack strict things. And the reason is, well, at least I think we'll only be able to unpack strict things. Maybe I have some ideas how we can unpack lazy things later. But the reason is, at least right now, is if you have a field that could be a thunk, we need the way to represent what value could be in that field, say an int, or the thunk in the same space. And the way we do that now is to have a uniform representation. We have a pointer which either points to the integer, the heap allocated integer, or the thunk, right, which is some other data structure that refers to the values captured in the thunk. So right now, yes, they need to be strict. I have some ideas. Maybe if you remind me at the end of the talk, I can give some ideas of how we could maybe unpack thunks. I had that idea yesterday, so it's not fully baked. Because I was looking at this slide, and I was going to say, like, why we have to have these strictness marks, and say, well, today you definitely have to have them, but maybe in the future we could do something different. Okay, good question. More questions? All right, so first thing is, this is terribly ugly. Like, I don't want to write this all over my code. So I made a change in GHG 7.8 where if you have a strict field like this one to the right that is of pointer size or smaller. So these are the ints, the words, the chars, the floats, the doubles, although they're 2 words on 32-bit platforms, but we count them, we do them even on 32-bit platforms, we automatically unpack them. So we ran some benchmarks. It has basically no effect on nofib because nofib has basically no strict fields. And it has some positive effects on some micro benchmarks. But the main gain is really that the syntax gets nicer. For example, none of our core libraries got faster because it already all had the unpack pragma. So it didn't really make a difference there. But it's a bit prettier. Now, we don't do this automatically for larger fields because in the case of an int, if you replace or anything pointer sized, if you replace the int with an unpacked version of the int, you use exactly the same amount of space. Before it was a pointer to something, right? That was one word, a pointer, and now it's int there. So you didn't grow something. So in the absolute majority of the cases, this should be faster or as fast as the old way. Now, when you get a larger structure like a pair or maybe a 5-tuple, now there's a trade-off. So if we unpack the representation, means we will have 5. If it was a 5-tuple, we'd have 5 ints, for example, in line with the constructor. If we didn't unpack it, we would have a pointer to something that has 5 values. That's fine, but what if we take this field that's larger and copy it into another data structure? Now there's a difference. So if we did the unpack thing, we had to copy 5 things into this other value, the other data structure. If you had a pointer, well, we only had to copy the pointer. So now we get this space copying trade-off. And we basically said, we'll leave it up to the programmer for now. In practice, I think you almost always want to unpack pairs. The cost for the CPU to copy this few fields is pretty small. There's also some other caveats regarding reboxing and laziness and stuff, so I won't go into that here. But for now, you have to be explicit if it's bigger than a pointer. If it's small, which is the fields you really want to unpack always, you get away without the unpack pragma. I think it was a success in the sense at least no one complained that their program got slower. So I think hopefully the assertion that they didn't hurt programs is true. We'll have to see if it made programs faster. There are 2 things that today can't be unpacked. Again, we'll come back to that in the last slides. But some types, like algebraic data types with more than one constructor, the reason is each constructor is a different size. So if you unpacked it, what size do we reserve in kind of the constructor we're unpacking it into, right? So we unpack something that has one constructor which has 1 field and one that has 100. Are we going to reserve 100 fields and just use 1? So for now, we don't unpack sum types. Also, there's a question of if you unpack the sum type, where would you put the constructor tag bit saying which constructor this is? So they don't get unpacked. And polymorphic fields, I think that's what you asked before. Today, the way we implement polymorphism is if you have a value of type A in a field, we always represent that with a pointer, right? That the representation is uniform, so it works for all A's, which means we don't have to do anything special to represent polymorphic fields. They're always a pointer. But since they're always a pointer, we can't unpack them. Okay, all right, so I'm claiming here that unpacking is a good thing, probably, right? So is it true? Is it better? So I have a bunch of examples here. So the first one is just a demonstration example I just tried the other night. So here's a list type specialized to int. I didn't put this bang on the int here because I want to talk about whether it's strict or not, because as I said, strict int fields in GT78 or later will be unpacked automatically, so I didn't want to confuse this. So this could be lazy or a strict int before 7.8 when those didn't get unboxed automatically. Right, so there's an int list, there's a representation, there's a header for the console, there's a pointer to the int that's allocated on the heap, and there's a pointer to the tail. And here's a trivial function to sum a list of integers. And then we have the contender, which is the same list with an unpacked int field. And the in-memory representation is what you see in the middle there. And there's a sum function to sum that. So if we compare these, so there's two things we want to try here. So first we want to compare the first representation to the second. And then the second thing we might want to compare is how we create the lists. Right? We have a lazy language. This was a lazy list. It was not strict in its tail component. So we can create that list in two ways. We can either create it lazily as we sum. Right? That would be maybe something we would typically do with lazy lists. Or we can try to create the whole list in memory first and then sum it. And we might expect that the latter might be slightly slower. We have more resonant memory. So in the measurements, which have, you can see these are the confidence intervals. So on my laptop, there's a little bit of noise in measuring, but it should be precise enough to say that the unpacked one is quite a bit faster in this case. This is neither the best nor the worst case for unpacking. So we're looking at a linked list. So there's still lots of pointers going on, right, between the const cells. So if you thought about, say, unpacking, if you're having an array of integers, right, or an array of pointed to integers, we would expect unpacking to maybe be a bit better because there's few other indirections around. But still, even for linked lists, it's quite sizable speed up. Okay, so that's a toy example. Who writes linked lists anyway? Let's look at some real code. So this is the map data type from the data.map module in the containers library. It's implemented as a size-balanced binary tree. So it's one of your textbook binary tree implementations. It has a size field, which is a type alias for int, which is the size, the number of nodes in this subtree. There is the key and the value. So maybe A should be in V, but we use A in the implementations for some reason. I don't know why. So there's a key, and the pointer to the key, there's a pointer to the value, there's a pointer to the left child or left subtree, and a pointer to the right subtree. Clear? Okay, so what happens if you don't unpack the size? It's the only thing we can unpack here, by the way, right? Because the K and A are polymorphic fields. We can't unpack those. And the map fields are some types, right? The map data constructor has two constructors, so they can't be unpacked. So the only candidate for unpacking is the size field. And how do we then, if we unpack it or not, we get these two representations, the unpacked on top and the non-unpacked, or the packed representation on the bottom. So how big a difference does this make? Single field, a single int field unpacked. So I have two benchmarks here, one for looking up elements and one for inserting elements in the map. If you look at, if you remove the unpacking, sorry, the unpacking is already there. So the first example is with the unpacking and then without. If you remove the unpacking, lookup didn't change. I checked the code. Lookup doesn't look at the size field, so that was kind of boring, assuming that the map was already allocated. You could expect, the reason I ran this lookup test at all, because I kind of knew that the size field wasn't used, is the map in memory, when it has this boxed size field, could be a bit larger because there's more memory allocated. There's some optimization GHG does with sharing small integers, I think, so that might have something to do with it. But anyway, in this case, lookup wasn't affected. We're not really using the field. Insert gets 24% slower if you don't unpack the size field, because we do two things with the size field on insert. We look at the size of the like we're creating a new node somewhere in the tree because we're doing an insert. So we look at the children, look at their sizes, which means we have to follow this pointer, right, to the int box, and then look at the int, sum these up, these two integers, create a new int box, put the value in there, and then use that in the newly allocated node. So that takes time. Both the allocation of this new box and following these pointers to look at the sizes of the subtrees. So it's about 24% for quite minor change. And again, this is not the best nor the worst case for unpacking. Binary trees are very much like linked list in that they're full of pointers everywhere. All right, let's look at something a little bit more modern. So in the last few years, there's been a resurgence in research on functional data structures because binary tree is not so good. They have too many indirections. They use too much space. They have too much overhead per element to storing all these pointers and headers. So there's been a new data structure called a hash array mapped trie. It's a bit of a mouthful. It basically is a tree with a higher fan out, typically 16 or 32. At each level, you have an array, which refers to all the children, and then another array. And then there's some clever tricks related to hashing to decide which element in the array you store your key and value in. The data type is a bit more complicated as a result. We're only going to focus on the bitmap index node. That's the node that occurs most often in that tree. For example, the collision node almost never happens. It's there because we need to handle collisions because we do hashing, but the bitmap index node is the most interesting one. All these fields are unpacked except for inside the array, the hash map cannot be unpacked because arrays don't unpack their fields and because it's a sum type. But otherwise, the bitmap is unpacked. The array data type itself, which you see defined down here, is unpacked. The hashes are unpacked. Arrays, the array data type uses a kind of primitive type of GHG, which is called small array, something added a version or two ago, I think, in GHG. It's just a kind of a data type that GHG provides to have an array. So it has some header, it has the number of elements, it has the pointers to the elements. It cannot itself be unpacked into something for maybe technical reasons. Anyway, it's always kept as a separate heap object. So the end representation for the bitmap index node here will be the unpacked bitmap, the pointer to the array, right? Because we unpacked away this array constructor, and in the array there's the size, and there's the pointer to the subtrees. If we look at the non-packed representation, it's quite a bit worse in this case. In the map case, there was only really one field that suffered, was the size field, and we got a little bit of an increase in size. In the bitmap index case, it's quite a bit worse because the tree got 50% deeper. Because now, without unpacking, well, first we have the bitmap field over here. It's wasting some space. But to get down to the next level, now we have to go to an intermediate array constructor. And from that, go down to the real array. And from that, go down to the next bitmap index node. So there's quite a few cache misses going down in this tree now, which is quite bad. So how big a difference does it make? In this case, for lookups, now we have a difference, a quite big difference, 44%, because the bitmap is very important for lookups. It's basically how we pick which of the subtrees we're going to go into. So we look at the bitmap, we do some clever population counts in it and decide which subtree we're going to pursue. So having that unpacked is important. Secondly, we look at the hashes. So somewhere in the tree we have the hash of the key stored. That's again just an int. We're going to look at this hash. If it's not unpacked, it's going to be slower. And then the arrays, right? This is more. On lookup, we have to do 50% more cache misses at worst. And for insert, it's also slow down. There's more to allocate in particular. And when we use more data, we use polluted caches more. I did an experiment here when I added this small array. So GHC used to have an array type which was slightly larger. Because it had the header, it had the number of elements, and it had a card marking table to say which part of the array might have been mutated. Anyway, it was slightly larger. So I added a small array, which is better for smaller arrays. So it takes slightly less space. And the speed up you see on insert is almost directly proportional to how much less memory you use. I don't know if that was just a coincidence, but it was eerily close. So there's good reason to believe that insert on this data type is almost completely memory bound at this point. The amount of memory we touches will be what decides the speed of the insert. So it makes a bigger difference here than it does on the binary tree, and again comes back to this intuition that the more dense something already is, the more you gain from unpacking, right? If you have a linked list which is very not dense already, unpacking something in the linked list just makes the other indirection more expensive, right? It's relatively more expensive. If something is already quite dense, like here we have arrays and fewer fewer levels to traverse in the tree, unpacking has a relatively bigger benefit. And taking that the whole way, right? Modern CPUs are the very best at completely flat arrays, where the values are actually stored in the array. Okay, so this is a long-winded way to come to the point of what should you do. So I guess the first maybe obvious point at this time is you should unpack stuff. Hopefully that's clear. But there's obvious stuff. Yes, you should unpack your integers. Storing an integer as a pointer to a heap allocated thing with a header that stores the integer is quite wasteful, right? It's 3 times the size for the integer plus 1 interaction. But what else? In addition to that, what do you do? So here's what I actually do. I have this 2-step process. I first estimate the current size and interactions to my data type, and then I find opportunities to make it smaller. So for the first point, I draw pictures. I draw exactly the pictures I've been showing you the whole presentation. I cannot. There's option 2, do it in your head, and that works. Like you can count the number of fields, add 1, and then you recursively count the number of fields and add 1. And that works. Just for me, I like the pretty boxes and the arrows. So I do that. But both ways work. Because when you count boxes, the number of boxes, the number of machine words you will use. Yeah?
Is there or should there be a tool to just calculate?
There are some tools. I think there's a function of Simon Marlowe added it called heap object size. I don't remember the name. You can call it on an object. It's a very unsafe function, right? And it will tell you some number. It's not really a productionized tool that you can point at your source code and says, for everything in this source file, here's the estimated sizes. That would be very useful. But that doesn't exist. There's a tool called Vacuum that can kind of draw these boxes and stuff for you. But whether it compiles or not always. It uses Haskell GUI libraries, so it doesn't always compile for me. There could be better tools. And I think it would be very useful if there were better tools. Okay, so once you estimated the space usage by counting the number of boxes, you should estimate the number of interactions. Again, you can count the number of arrows, or maybe find, if you have a data type that goes down like this, maybe you will want to count the longest chain. Depends what you care about. Each arrow is a potential cache miss. If you don't want to do the picture thing again, you can say, well, for every field I have that's not unpacked, that's going to be a pointer to something else, and count that way. I prefer the pictures again. Okay, so what do you gain? Well, just the rule of thumb, every time you unpack something, you save 2 words. You got rid of the pointer that needs to store, and you got rid of the header. So it's a two-word saving. What I already said, right, definitely unpack all the scalars, I think, right, the integers and the floats, etc. As I said before, there's this trade-off as fields get larger, unpacking might save you space, but you might lose in the copying if you ever take the field out and put it somewhere else. So you might have to copy, the individual members instead of the pointer. There you have to benchmark a little bit more. I think for things like pairs, I would always unpack them. And in fact, if you look at languages like C++, when they allocate pairs or they use pairs, they tend to use them inline, like by a value representation. So maybe there's some good evidence that other languages that have a value representation also choose to copy bigger things. In fact, when we work with C++ at Google, our style guide now recommends that we copy quite more often instead of, say, using pointers or references in C++. Because I think we programmers have a little bit of a skewed cost model for how cheap it is to copy versus how expensive it is to use more space. And for a CPU to copy a chunk of memory that's laid out flat is quite cheap. So you can usually unpack a little bit more than you think. Okay, so you got the simple cases. All your ints are unpacked, unboxed. But how can you expose more opportunities for unpacking? Then you have to be a little bit more clever. This a tool could probably not do for you. You have to look at your data type, and here's an example. This is from an old implementation of HashMap. It had a bunch of constructors. One of them was a leaf constructor. Since it could be hash collisions in the leaves, we store the key values as a list, right? Which was usually size 1, because we very rarely had collisions. But if you had collisions, that would be slightly longer. But since a list is a sum type, it can't be unpacked. So here's a little bit of ingenuity on my part, saying, well, it's always at least one element. And if you have a list of at least one element, you can make a new data type when you pull that element out. I call this full list here, and have the single element here, and then you have a list of potentially 0 more elements instead. By doing this, we have now created a type which is not the sum type. So that can be unpacked. Also by specializing this list to have, instead of having a triple of the key and value in the hash, we have like a specialized list here where the hash itself can be unpacked. And then we use it like this, which means that once you have loaded into memory your leaf heap object, the keys and the value and the keys and value is 1 pointer away instead of I think 3 steps away, and the hash is right there in the leaf value. So you're saving quite a few indirections. And you save 5 words per key value pair. This is, if you come from language like C++, you expect the usage, or they have like a hash tables type. You expect the memory usage to be a small constant higher than the storage need for the keys and values themselves, right? So if you have one word worth of key and 1 word worth of value, you hope that the space usage will be like 2.3 words or something like that, right? So we're still not quite there. Right? We saved 5 words, which is maybe more than twice that C++ would use in the end. But the point is, the overhead per key and value pair in a data type like this is very important, and it's really important to shrink it, because there are several applications, especially at Google, like MapReduce, where all the application does is it loads a huge table into memory, then it does a bunch of operations which does lookups in this table. The size of the overhead per key value pair decides how big a table you can have, and how much memory that's going to use, which in turn decides what your performance is going to be. So shaving overhead per key value pair is very important. I spend a lot of time in the unordered containers library to do just that. And I have a new version on the way that's going to shave off, I think, 2 more words. Show them. Okay, another trick. This comes from data parallel Haskell. Often when you have a sequence of composite types, so here we have a sequence of pairs, you can unwrap it and put it, turn it inside out and saying, I'm having a pair of sequences instead. This puts a little bit more burden on you as a programmer, because the representation on top made sure that the array, it's only one array, there's only one length. If you do this, it's now on your head to make sure that these arrays have the same length. But if you do this, the whole pair disappeared, and you saved, I think, 3 words of overhead for each element and 1 indirection. So DPH does this optimization automatically, I think, for data parallel Haskell code. I've done it manually in unordered containers to save some space. Okay, we're almost there. As last clever trick, I'll just be quick. This is kind of a different trick. It's not as much unpacking as it is caching. But the idea here is, in the byte string's representation is complex, involves lots of types, foreign pointers, etc. It involves this big sum type, and somewhere down in the sum type, we have the actual data we care about. Now, for byte string to be fast, we want to, when you pass the byte string around, to get from that heap object to the actual bits, the actual bytes, we don't want to have to traverse 3 pointers every time. So what we've done here, or not me, I don't know if it was Duncan or someone else who did this, is took some piece of data here, in this case the pointer to the actual bytes, and cached it much further up the hierarchy. Now, you probably won't work directly with adder or hash in your code, I hope not, but this trick can be applied to other things. If you have a value which is frequently accessed, it's far down somewhere where it's expensive to access, you can try to cache it further up. Now, since you're caching, you're taking a little bit of a correctness penalty as a programmer. You have to make sure that these are in sync, but that can help sometimes. Okay. All right, so I have about 6 minutes left. Yeah, question?
Just on the array case, was there no way to button the key values inside the array?
This one?
Previous slide.
So we would really like to. I think that's the starting point. So GHC has support for unboxed arrays of some primitive types. Like we can have an array of unboxed integers, etc. We don't, and also the vector package manages to do some unboxing for arrays by using a clever trick. in general, like we would like in general to be able to say array of unpack this stuff, right? The key and the value. We can't do that today. So I think our story for having really flat arrays is not complete, right? In a language like C, you can say array of my struct, right? And it has some representation for an array of a struct, which is, the elements interleaved, for example. We can't quite do that today. Any more questions? Good question. Yeah.
So is there a reason why you want a lazy infield?
In theory, it could be, right? If the correctness of your algorithm depends on having a lazy infield. I sometimes count the number of cases I found. Like I looked at text, I think a text, byte string, containers, under containers, hashable, and a few others. I haven't found one. I think GHC, I'm sure, uses a lazy infield for like counting the amount of heap space allocated, and they do some clever knot tying. And if you touch this infield at the wrong time, you will have a really bad day. But it's very rare, right? Things that are lazy are usually things that look like streams, so lists of things, right? Where you can kind of productively consume it in an incremental manner. Good question. All right. We have a couple more minutes. Let's talk about the future, aka the bonus slides. So someone, if you have this function, this is the lookup function on data.map, right? You give it a key and a map, and it gives you maybe the value depending if it's there or not. I'm a little jealous of imperative programming language here sometimes because they have null pointers. And there are two benefits of null pointers: permanent employment, right? And they'll also be more efficient because what they do with the lookup function is they return a pointer to the thing you looked up. And if that pointer is null, it wasn't there. Otherwise, you have to point it directly to the object. What we have to do here is we have to allocate the just constructors. What we return is a pointer to the just constructor, which takes base, which has a pointer to the thing we cared about. So we again have more indirections, and we also have to do this allocation. We have to create this just constructor, which typically is thrown away, right? Because you typically go case statement the next line. I was looking at some Rust and C++ code because they were adding an option type, like a maybe type to Rust and C++. And I was a bit curious, what implementation do they use? They don't have algebraic data types. So what they do is they have a tag, like a bool, and next to it they have a pointer, right? And they say, well, if the bool is true, the pointer points to something useful, and if it's false, it points to garbage, it's a null pointer or something like that, right? So that gave me the idea that there is a representation for multi-constructor type, for some types, that is flattened. So I said, like, well, we can steal that idea. That sounds maybe like a doable thing. So I'm now working on something called unpacking for sums. In fact, it's going to be implemented as something slightly more general. But the idea is there is a representation to unpack multi-constructor types by doing something like a C-style union. The representation is basically, well, we have a little integer that says which constructor you had. And you have a bunch of fields which are enough to represent any of the constructors. Which means that some of the time, some of the fields will have garbage in it, and some of the time they will point to whatever things that particular constructor used. This is down at the implementation level, right? We don't want to have these kind of fields at the Haskell level that point to garbage and segfault and stuff. But in the implementation, we can play this game saying, like, well, we're going to unpack this sum type, and we're going to you take the minimum amount of fields we can need to represent this. If you do that, now you can say, well, to return a just, in the back end, we're just going to return two values in two registers. One is going to be a bool, right, 0 for nothing, one for just, and the other one will be a pointer or not. And then we'll just have to do some clever rewriting. So when you do a case statement on this just constructor, we actually compile that to doing a case statement on these two small registers and checking the first one and maybe using the second one or not, depending what the first one was. Means that this function doesn't allocate anymore. Since this function doesn't allocate anymore, it doesn't have a heap check. So in the implementation, every function allocates usually starts with like an if statement, like a branch that checks, do we have enough space on the heap? Yes, good, no, go and garbage collect a bit, continue, right? So if you can turn a function that allocates to one that doesn't allocate, you can lose a bunch of branches in your code, which is good, right? Branches can be expensive. Maybe this branch is not super expensive. And then you allocate less. You just touch less memory is good, yeah. So there's an alternative unpacking story just for maybe, but because you could have a distinguished pointer that points, say, the null pointer, or point directly to the thing. By the way, it wouldn't quite work that way, because maybe it has a lazy field, so you actually need to point to either null or a thunk or the thing. But that could in principle work, but it doesn't work for either, because then, or like something like, either tuple int bool or foo, right? So the unpacking schema picking is good because it works for all sum types, no matter the number of fields. There's a simpler one or a different one that works for a sum type that has a single constructor with one field and then n number of nullity constructors. So we could actually do both. We can say, well, for the maybe case, we do the maybe even better thing. But what I'm implementing is this general unpacking for all sum types, which means that if you return an either, it again will be a bool and a single pointer, and we'll point to the left or the right value. I'm almost done. I'm running a bit low on time. So it's not going to make it into this GHC version because that's due so soon. But hopefully the next one. Last slide. Someone asked about unpacking polymorphic fields. This is the holy grail, right? One thing that makes, say, C++ faster than, say, Java, even though they're kind of imperative-ish programming languages, well, one is GC, that's one point, but maybe not as important as people sometimes think, is that C++, you can have a map of key and values, and the physical representation of that map is the key and the value stored in line with the data structure right there. Well, in Java or in Haskell, it will always be a pointer to the key and a pointer to the value. So again, you get an overhead of 2 words for the key, 2 words for the value. So that's 4 words overhead already, right? The top of C++, which just doesn't even have 1, maybe. And then these are indirections. So if we can unpack polymorphic field, would be really good. Also, the fact that we can't unpack polymorphic fields is really annoying, because let's say you've done all this beautiful unpacking. You have this data structure, foo, and inside it have a bar that's unpacked. Now you want to stick the bar in the map, right? Take out the bar and stick it in the map. Well, the map cannot contain unpacked things, so now we have to recreate this box for the bar. Allocate this box, copy the things into the box, put the box, inside the map, or have a pointer for the map for the box. So we have to recreate this box. So you can be nicely unpacked until you reach a data structure like a map, and then boom, all the allocation comes back and all the efficiency come back. So if you can unpack polymorphic fields, that'd be great. I have a vague plan. Basically, you do what C++ does, which it means code generation. Every time you see map used at a certain type, you generate a specialized data type instance at type int, and at type bool, and at type whatever it's used at. And then you have to also generate special code for insert. So that's basically what templates do in C++. They generate code and data layouts. OK, I'm running out of time, so I think this is all I will say about this, and I will take questions.
What's the relation with generic programming?
What's the relation to generic programming? I don't see one right now. Maybe there's one. I haven't thought about it. In the back? How slow would we get if we tried to do this polymorphic unpacking and generate all this code? Slower. I don't know how much. It is a lot of work, because the compiler now needs to carry around information saying that this data.map type must be specialized at every time it's used, meaning that you have to generate the extra code every time. So it's not even an optional optimization, right? You have to either always do it or always don't do it. Otherwise, you'll have an impedance mismatch between modules. So it's going to be the interface file, the .hi files will be a bit larger. I don't know. I can't quantify the cost. I'm sure there's going to be some. I've seen decrease in performance for unpacking. Not in my own code. What can happen sometimes is, you say you have a code base that doesn't do any unpacking, right? And you have fields that are copied from data type to data type. If you then unpack just one of them, what can happen is you take field from data type A, put it in, unpack it in here, and then you're going to put it over here, then you have to repack it again. So doing selective unpacking can sometimes mean that you pack and unpack and pack and unpack as you go between data types that are optimized in this way and data types who aren't. That's why I also recommend doing this by design, because one thing that happens to people sometimes when they try to fix these issues after the fact is they add a single bang pattern here, and that didn't help. Remove that, add it over here, didn't help, remove that. And it could be the case that you need both at the same time. And similar to unpacking, doing it selectively can mean that you get the pessimization in theory, at least, because you repack and unpack and repack. But it doesn't happen in like the byte string or text libraries or containers libraries. We unpack absolutely everything. Yeah, so what about Knuth and premature optimization? So first, Knuth has been, he wrote like this many volumes about assembly. So his definition of premature optimization and ours is probably a bit different. But if I abstract the question and say, is this premature optimization? I think not. Right? Doing the Hacker's Delight bit twiddling book and applying that, I think that would be premature optimization. It's the benefit is small, typically, and doesn't, the cost is not worth it. This is design to me, right? If I write code at Google to solve a specific task in C++, as it happens to be, like I think about these things up front. Like this will matter for whether my solution will be workable or not often, right? Because if I use a gigabyte of memory or 10, that's the difference between fitting on this machine and not fitting on this machine. So of course I cannot say you always should do this, but I think the space thing, as we see it, all these languages adopting a way to talk about value representation as kind of a fundamental thing, is a good evidence that this is not just kind of like a random, I hit it with this hammer right now.
What is your opinion about
What's my opinion about making laceliness optional? I have a summer of code student that has done that. So next Haskell version, you can at least put a pragma on top of a file saying all the bindings and data types in this file are strict by default. It's a bit of an experiment, right? It's not making Haskell strict, because all these libraries out there, they're definitely not strict, so it's not making Haskell strict. For performance, reasoning laziness is tricky.
Have you seen Edward Kmet's structs library, which is attempting to address many of the same issues that you talked about there?
Yeah, the question is, have I seen Edward Kmet's structs library? Yeah, we talked about it during ICFP. We're going to try to take what he did there and do something in GHC to be able to do what he did is there, I don't know if you saw the talk, he used like unsafe cores on top of a really unsafe pointer equality. This first time I've seen this combination. It's quite fearful to achieve what he wanted to do. I mean, we're going to try to do something more principled in GHC so you can have these kind of unpacked things in a slightly nicer way. Okay. I think that's it. Well, thank you very much.